Volume using known cross-sections. In this section, we will still be calculating volumes of solids. However, the major difference between this section and the previous two is that these solids are not created by revolving regions. Instead, we will be stacking common shapes on end, where the base of the shape will not be a set number but dependent on the function itself. It helps to see some pictures of how these solids look. So here we have one version where we have semicircles, another version where we have squares, another one where we have triangles, and another one with multiple rectangles. Below are some common shapes that we will see created in the cross-sections of solids whose volume will be found. We could have a cross-section that's a square, and its area would be b times b, or b squared. We could have a rectangle where the height is 1/2 of the base. So you would have 1/2 b times b, or which simplifies to 1/2 b squared. We could also have a semicircle, and the area of a semicircle is 1/2 pi times the radius squared. Well, if the diameter is the base, then half of that, or b over 2, will be the radius, and we got to square it. And when we square b over 2, we end up getting b squared over 4, and 1/2 times 1/4 is 1/8. So we have pi over 8 times b squared as the simplified area formula for a semicircle. In an equilateral triangle, the area of it will be 1/2 the base times the height. Well, the base will be b, but then the height will be b times the square root of 3 over 2. So that's how we get the square root of 3 over 4 times b squared. We could also have an isosceles right triangle where the hypotenuse is a base, and its area is 1/4 times b squared. We could also have an isosceles right triangle whose leg is a base, so we would have b as both the base and the height, so that would be 1/2 b times b, or 1/2 b squared. Below are some tips for solving the upcoming volume questions, or volume questions that involve cross-sections. Read the problem carefully, determine the bounds of integration, and decide which shape they are asking you to use. And finally, find the volume of one cross-section and integrate. Here's an example. Let the base of a solid be in the first quadrant bounded by the function f of x, which is equal to the square root of x, the x-axis, and the line x is equal to 9. Suppose that cross-sections perpendicular to the x-axis are semicircles. Find the volume of the solid. First, let's try to visualize what this is representing. So we have f of x is equal to the square root of x, and it's on the y-axis, which is kind of acting as the width of a tabletop, and the x-axis is the length, and the z-axis is coming up from the table to show that third dimension. So we have the square root function on the xy axis, or on your desk, basically. And then we're making semicircles pop out of the desk. And we have stacked semicircles from x equals 0 to x equals 9, whose bases or diameters are defined by our square root function. The volume of a single semicircle, where h is the thickness of each one, is that the volume of the semicircle is equal to 1/2 pi r squared times the height. In this case, the radius of our semicircle is halfway between the x-axis and the square root of x function. So that's why we have 1/2 times the square root of x. Since the diameter is represented by the function, like you can see the little semicircles, I could draw straight lines here, and those would all be diameters. And the radius is half of each diameter. The next step is to set up the integral for the infinite number of semicircles within the interval from 0 to 9. So that's the 1/2 pi. Now the radius is that integral from 0 to 9, and our radius was 1/2 times the square root of x being squared. and then the height is our dx. So now let's try to work this out. So we're still going to have the 1/2 and the pi out in front. Then we have the integral from 0 to 9. If we square this, it's going to end up being 1/4 times x, and we're going to integrate it with respect to x. So we have 1/2 times pi, and then when we integrate 1/4 x, it'll be 1/4 times 1/2, or 1/8 x squared. And we can now evaluate this from 0 to 9. So we have 1/2 times pi, and if we square 9, we get 81. So we get 81 over 8 minus 0, and 81 pi over 16 is going to be our final answer for the volume. Here's another example. Let the base of a solid be in the first quadrant, bounded by the function y is equal to 1 minus x squared over 4, the x-axis and the y-axis, and suppose that cross-sections perpendicular to the x-axis are squares. Find the volume of the solid. First, let's visualize how that appears. As you can see, we have stacked squares from x equals 0 to x equals 2, whose bases are defined by the function 1 minus x squared over 4. The reason the region extends all the way to 2 is because that is where the function and the x-axis, one of the other bounds, intersect with one another. The volume of a single square is s squared times the height. And if we substitute our function in for that side length, or the base, we would get that the volume of our square is equal to 1 minus x squared over 4, quantity squared, and then again times the height. And again, s is the base being represented by the function, and h is the thickness of the cross-section. We are not rotating any area, so we can write out the integral as shown below and evaluate. The volume is equal to the integral from 0 to 2 of our side length, 1 minus x squared over 4, quantity squared, times the height, which is dx. And we can simplify this to be the integral from 0 to 2 of 1 minus x squared over 2 plus x to the 4th over 16. And again, we're going to integrate with respect to x. And when doing so, we'll get x minus x to the 3rd over 6, because 1/2 times 1/3 is 1/6, plus x to the 5th over 80. And we can evaluate this from 0 to 2. So we're going to have 2 minus 8/6 plus 32 80ths. You could simplify it if you wanted to be 2 minus 4/3 plus 2/5. And when you evaluate that in a calculator, you will end up getting 1 and no tenths, but the 6 in the hundredths place continues to repeat. So if you round it to the nearest thousandth, you end up getting 1 and 67 thousandths. Now some may be asking, what happened to the pi? Before, whenever we were finding the volume, we were multiplying by a pi in front. Why don't we have it this time? Well, since the solid is no longer cylindrical or conical, for that matter, it could either look more like a cylinder or look more like a cone, depending on what functions you had there. The pi is then removed, and we make it resemble the area of a square, which again is that side length squared, and then the height of that cross-section is the dx. Here's another example on using cross-sections. Let the base of a solid be in the first quadrant, bounded by y is equal to x to the 3rd power, the x-axis, and the line x is equal to 1. Suppose that cross-sections perpendicular to the y-axis are equilateral triangles. Find the volume of the solid. First, let's try to visualize how that appears. If we have the x-axis here and the y-axis going this way, and the z-axis kind of coming up and partially out of the page, we will end up getting these triangles that are showing up coming out of the page, and they're stacked from x equals 0 to x equals 1. Well, where'd the 1 come from? Well, it's actually where x cubed and x equals 1 are equivalent to one another. So you can always use the bounds to determine your lower and upper bounds for integration. And the bases of these triangles are always being defined by the function. And then since the cross sections are perpendicular to the y-axis, we need to express the function in terms of y. In other words, we need to write y is equal to x cubed to make x a function of y. So in order to do that, we are going to cube root both sides, and we will get that x is equal to the cubed root of y. You could also write it as y to the 1/3 power. The area of an equilateral triangle can be found using the formula a is equal to the square root of 3 over 4 times b squared. But where did this come from? Some of you may be asking. Well, remember, whenever you have a triangle, its area is 1/2 base times height. Well, we know our base is b, but then an equilateral triangle is special in that all of the original angles are 60 degrees. And we know this side's b and this side's b, and if we drop down an altitude, it splits the 60-degree angle up into two 30-degree angles. So we have a 30, 60, 90 triangle. And if we know the whole length is b, we know that the small leg is half of b. And then we could use Pythagorean theorem to solve for h. We would have 1/2 b squared plus h squared is equal to b squared. And if we were to solve that, we would end up getting that h is equal to square root of 3 over 2 times b. So if we substitute this h value into our area of a triangle formula, we end up getting 1/2. Our base is still b. Then our height is square root of 3 over 2 times b. And when we simplify, we get square root of 3 over 4 times b squared. And again, b is the base represented by the function, and that is the distance between the two functions in our example. So instead of b squared, we can substitute in the outer function 1 minus the inner function, the cubed root of y, and we're squaring that. We are not rotating any area, so we can write out the integral as shown below and evaluate. The volume is equal to the square root of 3 over 4 from our area formula can be pulled out of the integral because it's not going to change. And then we have the integral from 0 to 1 of our b squared, and that b is 1 minus the cubed root of y squared. And then remember, the thickness of each cross section is dy, because again, we're making it perpendicular to the y-axis. So if we expand and finish solving this, we will have the square root of 3 over 4 times the integral from 0 to 1. And if we expand out 1 minus the cube root of y and we square it, it becomes 1 minus 2y to the 1/3 power plus 2y to the 2/3 power. And again, we're integrating with respect to y. So that's going to be the square root of 3 over 4 times, when we integrate this, we will end up having y minus, we'll have y to the 4/3, and we have to multiply 2 times 3/4, which is 3/2. Plus, we'll have y to the 5/3, so we need to have 3/5 out in front. And again, we are going to evaluate this from 0 all the way up to 1. Well, all of these will be 0 when we substitute that value in. So we really just have to evaluate this at 1 and finish. So that'll be the square root of 3 over 4 times 1 minus 3/2 plus 3/5. And when we find the common denominator of 10, we'll have 10 over 10 minus 15 over 10 plus 6 over 10. So that ends up being 16 over 10 minus 15 over 10, which is just 1/10 remaining. So we have the square root of 3 over 4 times 1/10, and that's how we end up getting that the final volume is the square root of 3 over 40.